This is the video solution to problem number 1. So I've got this geyser at the bottom, and I want to figure out how much pressure is generated at the bottom to send the water all the way up to a height of 75 feet above the ground, or 75 meters above the ground. So when I'm looking at this, I can think, all right, well, my first choice might be force. But when I think about the force to do this, I need an area, I've got to have a force, I've got to have pressure, and there's all kinds of things that I don't have. So if I look at it, you can see where I've drawn a picture on the right. On the picture on the right, I've got kind of a streamline over there. So with this streamline of flow, I'm starting down low, and then going all the way up to the maximum height. The maximum height we're calling apogee. So really what I'm looking at is I'm looking at the energy it takes at the bottom, the pressure potential energy, all the way up to get it up to the maximum gravitational potential energy. Now at its maximum height, the speed is going to be 0 because it won't go up any higher. That's its maximum point. And I also know the pressure at the maximum height because it's in the air, so the pressure is going to be atmospheric pressure. Alright, so let's look at this as an energy, conservation of energy problem. In other words, Bernoulli's principles, or Bernoulli's equation. First, I'll start with the givens in the chamber. I know I've got the pressure potential, I know the velocity is 0 and the height 0. So that means my kinetic energy, my potential energy over volume is going to be 0. And then if I look at the apogee, I know the velocity is going to be 0, the height is going to be 55 plus 75 meters from the ground up and then from the ground down to the chamber. And the atmospheric pressure is going to be 1 atmosphere of pressure. If I look at it in terms of energy, I set it up, I've got the pressure, potential energy in the chamber, I've got the kinetic energy per unit volume in the chamber, I've got the potential energy per unit volume in the chamber, and that's equal to the pressure potential energy at apogee, the kinetic energy per unit volume at apogee, and the potential energy due to gravity per unit volume at apogee. So as I'm looking at all this, I'm going to start analyzing what's going on. In the chamber, the water's not moving. So this is deep down inside the chamber, not the top of the chamber where the water comes out. You say, well, the water's coming out there. It is, but that's not what I'm looking at. I'm looking at the pressure deep down inside the chamber. So deep down inside the chamber, it's not moving. Deep down inside the chamber, well, that's going to be my lowest point. And the pressure, that's going to be 1 atmosphere of pressure at the top at apogee. And at the apogee, it's not moving anymore. It's reached its highest point, so I know the kinetic energy per unit volume is going to go away. And since it is the highest point, it's going to be all gravitational potential energy per unit volume at apogee. So when I set this up, I got the pressure potential in the chamber, and that's equal to rho GH, which is the potential energy per unit volume, plus the pressure potential energy all the way up there at apogee. At this point, I can put in my numbers because I got my variable all isolated, and then do the math and get the final answer.